Hello again, Lou McIntyre with some more insights into the special theory of relativity. Let's get into it. In this video, we will talk about whether the velocity triangle is just a useful tool or can be observed in some reference frame. This, of course, is the velocity triangle. Two reference frames propagate at the speed of light each, as does all matter, defining their directions of propagation in four-dimensional space as their time axes unique to their reference frame. Relative velocity disappears as an independent variable, becoming a projection of one body's temporal velocity onto the temporal axes of the other and the spatial axis through the Brem velocity angle beta, the difference between their relative directions of propagation. The spatial component of NS1 has a velocity V over C equal to the sine of beta. Convenient and easy to use, but is it real or just a useful mathematical abstraction? Let's find out. Let's set a third reference frame S3 in motion in the y direction to the XC of NS2. The beta is subscripted with the reference frame to which it belongs and the reference frame to which it is connected. The velocity angle beta 1, 2 between S1 and S2 is going to be kept constant at half the speed of light. The velocity angle beta 3, 1 between S3 and S1 is the independent variable. This angle lies in the YCT plane, so S3 will observe S1 receding in the y direction only. S3 will see S2 receding with velocity in the y direction due to S3's velocity with respect to S1, and in the x direction due to S2's velocity with respect to S1. S1's velocity angle beta 3, 2 is the arc BC and is a function of beta 1, 2 and beta 3, 1. This looks like it would be a major headache to solve with algebraic form of the Lorentz transform, but as we are about to see, it is relatively easy to solve trigonometrically. This will all play out on the surface of a sphere. The spherical triangle ABC is a very familiar one to me. It is identical to the navigational triangle. I, in times past, was an airborne navigator in the days before GPS, using that triangle to determine great circle bearings and ranges on the surface of a globe, and bearings and elevations of stars for celestial navigation. BA and CA are the co-latitude of S2 and S3, 90 degrees minus their latitudes, corresponding to beta 1, 2, the angle AOB at the center, and beta 3, 2, angle AOC at the center. CB is beta 3, 2, the angle COB. The angle ACB is the bearing of B from C, the angle alpha, measured between CA and CB. For terrestrial navigation, multiplying the angles AB, CA, and CB by the radius of the Earth yields great circle distance. For our purpose, the surface of the sphere is the locus of all points of a single common proper time. Therefore, this sphere is expanding with each click of the S3 clock. We're going to set the radius at CT3 equal to 1 unit of time for our solution. Again, distance is the velocity angle multiplied by radius CT3. Angle L in the range equation is DOE, the difference in longitude between B and C. In our case, it is always 90 degrees, the angle between the X and Y axes. This permits some simplification of the range equation, as cosine L then becomes 0. Trig identities permit this expression to be expressed as the sine of beta 32 equal to v32 over the speed of light. For small recessional velocities of S3, the sine of beta 32 tends toward the vector sum of the sines of beta 12 and beta 31, since the product terms in the range equation become very small. Beta 32 tends toward beta 12, and the bearing angle tends toward 90, as beta 31 goes to 0. On the other hand, at high recessional velocities between S3 and S1 approaching the speed of light, the sine of beta 31 tends toward unity. Beta 32 tends toward beta 31, and alpha tends toward beta 12. Now let's see how this plays out on S3's XY plane. We place S3's XY plane around its timeline. As time marches on, S1 and S3 will map out trajectories on the S3 XY plane, the sines of their beta multiplied by time in S3. S1's trajectory is in the Y direction only, while S2's is in the X and Y direction, the total distance S32. The bearing angle determines the X and Y components of S32. We're going to use V31 as our independent variable and see how the trajectories shape up at time CT3 equal to 1 for various velocities. In our first case, we set V31 equal to 10% of the speed of light. This gives a velocity V over C between S3 and S2 of 0.507. Just a few tenths of a percent different from their vector sum of 0.509. The bearing angle alpha is 80 degrees. The distances are just the sines of beta 31 and 32 multiplied by CT3 equal to 1. The Lorentz transform affects distances only in the direction of motion. Therefore, the x32 component of total distance S32 is 0.5 at time CT3 and is not affected by this or any other value of V31, as that velocity is normal to V31. Alpha decreases as we increase the recessional velocity to half-life speed. And the total velocity between S3 and S2 is now much less than the vector sum of sine beta 31 and sine beta 12. The x component of V32 remains 0.5. Now we increase the recessional velocity to more than 99% of the speed of light, a velocity angle of 85 degrees. The velocity triangle emerges on the xy plane, with alpha becoming very approximately beta 1, 2. And the length of y31 and s32 becoming approximately equal, 0.9996 and 0.997. Equal proper times in S1 and S2 map out to very nearly equal total velocities and distances in S3. As a result, those proper times map to nearly simultaneous events and observation in S3 because their respective Doppler shifts and distances are approximately equal. We locate a point on the y31 axis equal to S32 at CT3 equal to 1. We erect a temporary x-axis at y31 equal to S32. Now we advance time CT3 to 1.154 and project S32 at CT3 equal to 1 to intercept the Y3 axis at 1.149 as 1 over the cosine of alpha. Y31 multiplied by V12 yields a displacement of 0.574. Then we proceed from the end of S32 in the direction of the temporary x-axis, intercept it, then an equal distance in the direction of y3 to locate the transformed x32 coordinate. Thus, we have performed the Lorentz transform of 0 to 1 to 1.149, 0.574, approximately the correct answer, all based on the xy plane of S3. We have captured and observed not only the velocity triangle, but also the methodology that I have developed for solving it. In summary, an object in motion at right angles to two bodies, also in relative motion, will observe their velocity triangle mapped out with increasing accuracy as the recessional velocity away from them approaches the speed of light. This implies that the velocity triangle is not only a useful analytical tool in mathematical abstraction, it may be the fundamental physical process being described by the Lorentz transform. I didn't know where I was going when I began this analysis many years ago. I was, to say the least, stunned that it worked out almost immediately. It certainly made me believe that my simple tool is more than just that, and maybe a wholly new insight into the special theory. I hope you enjoyed this presentation and perhaps learned some things you didn't know about the special theory and the Lorentz transform. If you want to learn more, read my book, Writing on a Light Beam. You can purchase it on Amazon or via my website shown. And don't forget to press the like button. It helps make this YouTube presentation more widely available. Thank you for watching.